You know, every single day, probably hundreds of times a day, we send information flying across the world in just an instant. But what is actually going on behind the scenes? Well, let's pull back the curtain and follow the incredible, invisible journey your data takes from the moment you hit send to the second it pops up on someone else's screen. So you've just fired off an email, maybe a text message. It feels completely instantaneous, right? But it's not magic. Nope, it's a super organized, lightning-fast trip across a massive global network, and we're going to break down that entire trip for you step by step. Okay, so the whole journey kicks off with a pretty simple problem. Your data, whether it's a photo or a long email, can't travel in one giant piece. It's just way too big. So before it goes anywhere, it has to be packed up really carefully. Imagine trying to mail an entire car. You can't, right? You'd have to take it apart, put the pieces in separate boxes, and ship them. Well, digital information works the exact same way. Your message or your video gets broken down into these small, super efficient chunks we call packets. You can think of each packet as its own little self-contained piece of a jigsaw puzzle. It's designed to be sent across the network and then, on the other side, be perfectly reassembled. I mean, this simple idea, breaking things down just to build them back up again, it's pretty much the foundation of the entire modern internet. And just like a package you'd get from Amazon, each one of these data packets has a very specific structure. It's not just the data itself. It's wrapped up in all the information it needs for a successful delivery. So let's break down this digital parcel. First, you've got the header. That's the shipping label. It has the sender and receiver's IP addresses, which are kind of like digital street addresses, plus a packet number so everything can be put back in the right order. Then there's the payload. That's the good stuff, the actual piece of your message. And finally, the trailer. This acts like a quality seal, and it contains data to check if the packet got scrambled or damaged along the way. Now, here's what's really cool about all this. The packets don't all travel together. This is a process called packet switching. The network is constantly finding the most efficient route for each individual packet. And the brilliant part about this is that it makes the internet incredibly resilient. You know, if one route gets jammed up with traffic or just fails, the packets just find another way. The system doesn't break, it just adapts on the fly. So our little packets are all packed up and addressed. Now it's time for them to hit the information superhighway. And just like real roads, this digital highway has different lanes and, yep, traffic rules that our data has to follow. The simplest path is what we call serial transmission. Think of it like a single-lane country road where all the data bits travel one after another in a line. It's actually perfect for long distances. But for pure speed, you've got parallel transmission. This is your multi-lane highway, sending lots of bits all at once. It's way faster, but it really only works well over short distances, like from your computer to your printer. And every highway needs traffic rules, right? So Simplex is basically a one-way street. Data only goes in one direction. A great example is your keyboard sending commands to your computer. Then you have Half-Duplex. This is like a single-lane bridge where cars have to take turns. Data can go both ways, just not at the same time. A walkie-talkie is the perfect example. And finally, Full-Duplex. That's your proper two-way highway where data flows in both directions all at once, just like a natural phone conversation. Now, this journey, it can be a little rough. Network issues or interference can corrupt data packets. So a really crucial part of the process is quality control, making absolutely sure that what arrives is exactly what was sent. I mean, this is a super important question. If even one tiny bit of data gets flipped from a 0 to a 1, it could corrupt an entire file or just garble a message. So how does the system even know that an error happened in the first place? It knows because it has a whole team of built-in digital inspectors. There are quite a few methods, from a simple echo check where data is just sent back to the source to be compared, to a much more sophisticated system called Automatic Repeat Request, or ARQ, that uses acknowledgements to confirm a safe arrival. But to really get the idea, let's look at a couple of the most fundamental techniques. A parity check is a really simple but also really clever method. Before sending anything, the sender and receiver agree on a rule. Let's say even parity. This just means that every byte of data has to have an even number of ones. So the sender adds one extra bit, the parity bit, to make sure it does. When the receiver gets the data, it just counts the ones. If the count is odd, it knows something went wrong and asks for that packet to be sent over again. So for example, if the byte that arrives has an even number of ones, just like it's supposed to, the check passes. Easy. But if a bit got flipped and now the count is wrong, the parity check fails. The receiver spots that error instantly and basically says, hey, send that one again. It's a surprisingly simple and effective system. A checksum is kind of like doing a math problem to verify your work. The sender runs a calculation on a block of data, and it produces a unique number. That's the checksum. It sends this number along with the data. The receiver on the other end runs the exact same calculation. If it gets the same checksum, the data is good to go. If not, you guessed it, it asks for a resend. Now, you might be thinking this is all pretty abstract computer science stuff, but you actually interact with a form of this every single day. That barcode on your groceries? Yep, it uses a check digit for error detection. So, here's the deal. That very last digit on a barcode, it's not random at all. It's a check digit, which is basically a real-world checksum. As you can see here, its value is calculated from all the other digits. So when a cashier scans it, the register does the same calculation in a split second. If the numbers match, the scam works. If not, you get that dreaded error beep, which actually prevents a mistake. It's error checking out in the wild. Okay, so our data has been packaged, it's been sent, and it's been error checked. But there is one more vital step, especially when we're talking about sensitive information: security. We have to make sure no one can eavesdrop on the journey. And this is where encryption comes in. It's basically the art of scrambling data into an unreadable code, which we call ciphertext. Only someone who has the correct key can unscramble it and read the original message. It's really the digital equivalent of an unbreakable lockbox. So how do you do this? Well, one common way is called symmetric encryption. It's really straightforward. There's one single secret key. The sender uses it to lock the data, and the receiver uses the exact same key to unlock it. It's simple, it's effective, but it does have one big challenge. How do you securely share that one key in the first place? Well, that challenge is solved by a much more robust method: asymmetric encryption. Here we actually have two keys, a public key and a private key. The public key, which is for locking data, can be shared with absolutely anyone. But the private key, the one for unlocking, is kept completely secret by the recipient. So you can use my public key to send me a secure message that only I can open with my private key. This is the foundation of most of the secure communication we rely on online today. And that's really the final piece of the puzzle. So let's put it all together. Your data gets broken down into packets, sent down the digital highway using different traffic rules. It's checked for errors to make sure it's intact. And finally, it's locked with encryption for security. This entire incredibly complex journey happens in the blink of an eye every single time you go online. So what's next? This amazing invisible journey is literally the backbone of our modern world. And as we demand more speed and more security for everything, from streaming movies to global finance, it really raises a fascinating question. How is this fundamental process going to have to evolve to meet the demands of tomorrow?